This is a lab exercise captured on video on the topic of range Doppler processing, taken from the Lab 3 of the Dreamcatcher ME1510 University Courseware. We are going to explore the basic SAR imaging concept and SAR processing steps, based on range Doppler algorithm, to perform azimuth compression for SAR. To get the most out of this lab exercise, you should view the video along with the lab sheet. Please download the lab sheet from this link. You may want to pause this video to read the lab sheet first, before proceeding with the video streaming. Synthetic aperture radar is a form of side-looking airborne radar system that uses the motion of the radar antenna to provide fine spatial resolution in its along-track direction. Figure above shows the generic SAR imaging geometry. As the aircraft move along the flight path at constant altitude, a pulse or chirp is transmitted at each position, and the return echoes pass through receiver and are recorded digitally. X direction is a cross-track, or range direction, which perpendicular to the flight path. Y direction is a long track, or azimuth direction, which is flight path of the aircraft. Z direction is altitude of the flight. The slant range R is defined as R equal to square root of x square and z square. The transmitted SAR signal can be expressed in equation 1. After demodulation, the backscattered signal received from a point scatterer, located at arbitrary coordinates, is given by equation 2. After transforming the time to slant range domain, backscattered signal can be rewritten as equation 3. After superimposed all the elementary returns from the illuminated surface, the raw signal equation can be expressed as equation above. Function f is the surface reflectivity pattern, and function SR is the impulse response of the system. For example, the return due to a unity point scatterer. The SAR imaging challenge is to design an appropriate filter, such that we can recover the best estimate of function f, based on the received signal S. The equation above shows the result of Fourier transform of equation 3, in spatial angular frequency domain. In the early SAR development, the range Doppler algorithm has been the basic of most precision SAR processor. The RD algorithm is based on the series expansion of the transfer function phase in equation 5. The equation above is formed by using a Taylor series expansion on range frequency. The first phase term alpha represents an azimuth chirp function that is responsible for azimuth compression. As for second phase term beta is often referred to as range migration correction factor. The third phase term gamma is usually referred to as secondary range compression factor. These phase terms are used in the RDA processing. RDA consists of 5 processing steps. Initially, SAR signal is expressed as function S. RDA begins with range compression. In this process, raw signal is Fourier transformed and multiplied with range reference function P, which is known as range match filtering. After range match filtering, range inversed Fourier transform is performed. The second processing step of RDA is azimuth Fourier transform. In this process, SAR signal is azimuth Fourier transformed into range Doppler domain. The following process is range migration correction. Range interpolation operation is performed in range Doppler domain. The next process is azimuth compression process. In this process, azimuth match filtering is performed. The final process is azimuth inverse Fourier transform. The SAR signal is azimuth inverse Fourier transformed back into range time and azimuth time domain. The output of the RDA is 2D SAR image, and can be expressed as function f. In this lab experiment, we are going to measure point targets by using the Dreamcatcher ME1510 radar imaging training kit and MATLAB to perform azimuth compression. The ME1510 training kit consists of embedded imaging radar module, linear scanning platform, horn antenna, corner reflectors and PC-based GUI software. A linear scanner is provided as the moving platform for the imaging radar system. This enables the radar training kit to perform translational scanning mechanism for imaging radar operation. The imaging radar module consists of a C-band RF transceiver and a radar processor. The radar processor consists of a data acquisition unit and high-speed single-board computer for raw data digitizing, as well as SAR signal processing. A PC-based GUI software is also provided, allowing user to configure the radar for various operations. A C-band horn antenna is employed to perform monostatic radar configuration. Two types of corner reflectors, that is trihedral corner reflector and dihedral corner reflector, are included as external man-made targets for radar measurements. Before the measurement begins, connect the SMA connector of ME1510 imaging radar training kit to the horn antenna via RF coaxial cable. Power on the imaging radar kit. The linear scanning platform will perform an auto-homing sequence as part of its initialization process. Then, boot up the high-speed single-board computer in the embedded imaging radar module. On remote computer, set the IP address and the subnet mask of the Ethernet port to 192.168.1.101 and 255.255.255.0, respectively. At the top right corner of the GBSAR GUI, ensure the IP address is set to 192.168.1.100 in the TCP IP setting column, and press the Connect button. The status of the TCP IP will change to 192.168.1.100 connected, whereas the status of the RF module will change to ready. Place two external targets about 3 meters away, at the middle of the scene to be scanned. Set the spacing between them, d, about 0.4 meter along azimuth direction. Press the home button to move the antenna back to its home position. Once ready, press the scan button. Add a description for this experiment in the Confirm Scan window, and start the scanning process by clicking the OK button. The range profile for each of the scan will be recorded and displayed in the GBSAR GUI window. Once the scanning process is completed, the measurement data will be saved in the subfolders, with the naming format based on the local date and time of the remote computer. Go to the menu bar, click on Tools followed by Quick View, then SAR Image, to display the synthetic aperture radar image in a 2D plot. Next, go to the menu bar, click on Tools followed by Quick View, then RAW Image, to display the real aperture radar image in a 2D plot. It is observed that the SAR image is able to focus the targets for azimuth spacing of 0.4 meters. On the other hand, RAW image cannot correctly separate the two targets for azimuth spacing, d equals 0.4 meter. It is because, in RAW configuration, the azimuth resolution is about 0.8 meter, while in SAR configuration, the azimuth resolution is about 0.2 meter. Now, repeat the experiment by placing the external target at different spacing of d equals to 0.2 meter, in range direction, while maintaining the spacing of 0.4 meter in azimuth direction. First, we select SAR Image Quick View, to display the synthetic aperture radar image, for the two targets with azimuth spacing of 0.4 meter, and range spacing of 0.2 meter. Then, we continue to display real aperture radar image for the same targets. It is observed that the SAR image is able to focus the targets for range spacing d, larger or equal to 0.2 meter. On the other hand, RAW image is also able to separate the two targets with range spacing of 0.2 meter. It is observed that both the RAW and the SAR configuration are able to differentiate the two targets located at range spacing of d equals to 0.2 meter. Hence we can say that the range resolution of an imaging radar is independent of the signal processing technique used. In this exercise, we will use MATLAB software to perform azimuth compression. We begin this exercise with writing the codes in MATLAB editor to read the header file and raw data file. After that, save the file as sar.m, in the same folder as the folder that contain the header file and raw data file. These codes will extract the SAR processing parameters from the header file, and SAR data from the raw data file respectively, to the MATLAB workspace. Next, write the codes for radar signal processing, using range Doppler algorithm in MATLAB editor. Create two sets of new arrays, range domain arrays, and azimuth domain arrays, to represent the range's and azimuth's distance and frequency, respectively. Continue with the code, to only process the data within desired range. Then, save and execute the M file in MATLAB command window. After that, type size, S, in MATLAB command window, to check the size of the array after removing the unwanted range. Next, define the variables used in azimuth domain arrays. The Doppler center frequency is set to 0, since the speed of antenna travel is very much smaller as compared to the speed of light. Zero padding is performed, to increase the number of azimuth samples for a total length of L. Then, write the codes for secondary range compression, as the input data is already in range compressed form. Next, perform azimuth compression in range Doppler domain. Save and execute the M file in MATLAB command window. Then, check the size of the input data array after zero padding. Next, truncate the azimuth data, to remove the data outside of the observation range. Then, save and execute the M file in MATLAB command window. Type the command following, in the MATLAB command window to display data as 2D image. Use function surf to create a 3D contour plot, and then project it onto a 2D plane for viewing. For more information, please refer to Lab 2, Section 4. Save and execute the M file in MATLAB command window. Display SAR image in log scale. Then, save and execute the M file in MATLAB command window. Determine the 3 dB range resolution, and the azimuth resolution. Save and execute the M file in MATLAB command window. In this lab session, we have learned about basic SAR processing steps, based on range Doppler algorithm. Performed raw data acquisition, and compared the real aperture radar and SAR images. Performed RDA processing on SAR data, to generate a 2D SAR image. Thank you for viewing ME1510 lab on video. For more labs on video, please visit